Hello, welcome back to 10-Minute Science, where we pick a topic, we dive in, we learn about something amazing in 10 minutes or less. Remember, plus or minus 12 or 13 additional minutes. So today we're going to talk about plasma, often called the fourth state of matter, solid, liquid, gas. Then we have plasma. Comprises something like 99.9% of all of the visible matter we can see in the universe. And so it's very, very common. It's all around you. And so we're going to dive in and talk about plasma, what it is, how we can use it to generate power and things like that in nuclear fusion reactors and so on. So first of all, what is a plasma? A plasma is just a gas, just like the gas in this room, but instead of neutral atoms, we've added enough energy to the gas to make it so hot that the electrons, at least some of them, become detached from the atoms. And so you have free electrons running around the plasma, and then you have the positively charged ions left behind from the atoms that were there, and you have these charged species running around in the plasma there. So it's essentially an electrically conductive gas. It's a gas that conducts electricity. Now, if we stop there, it doesn't sound so interesting. Let's dive in a little bit deeper. Let's take a look at some examples. The first example is the famous plasma ball you can see. So in this little image here, you can see the tendrils of pink and bluish kind of light reaching out, and you can notice sort of the instability there. In other words, the plasma is not a fixed object. It's always moving and dancing, and we're going to talk about why that is. It turns out that this behavior happens because of the charged nature of the electrically conductive gas. So because it's charged is why it moves like this. And that actually makes it really hard to contain a plasma for something like a fusion reactor. That's what makes the challenge of nuclear fusion actually so difficult. We'll talk about that a little bit later. So beyond that, the next example of plasma I have for you is something you've seen. It's called lightning. The brilliant flash of light that we see in the sky during a thunderstorm, it's actually breaking down the gas particles between the cloud and the ground, or between two clouds, generating a ionized gas, a gas where some of the electrons have been stripped off of the atoms, and so that's called lightning. Another example from everyday life would be like a neon sign. Any of those signs you see, now open or come inside or something like this, where it's glowing orange or even glowing blue and other colors, that's actually a plasma inside of there. We run an electric current in there, and the electric current strips off the electrons, and we see the resulting glow. We're going to talk a lot more about the glow here in just a few minutes. Finally, the next example I have is the famous aurora that you see at the poles of the Earth. Now, this aurora is because of the solar wind hitting the Earth, interacting with our magnetic field and colliding with the atmospheric gases we have in the top of the atmosphere and creating this dancing display. It looks a lot like a plasma ball because that's basically what it is. What we're seeing is the atoms of our own atmosphere lose their electrons and recombine, giving us this light. But notice that the aurora is also dancing and waving. It's not static. I'm bringing this up again and again because it's a very important characteristic of plasmas that they are very complex to model and to control and contain. So we're going to talk about that later. Another example of plasma from everyday experience is a candle flame. We don't typically think of a flame as being a plasma, but it is, because the chemical reaction going on here involves a transfer of electrons. There's oxygen, and then combining with whatever the fuel is, there's a transfer of electrons there, or electrons are basically moving around, and the thing gets very, very hot. And so when things get hot like this, there's always going to be some fraction of these electrons which can become detached from the atoms, and then of course recombine. And when the electrons come back into the atom and recombine with the atom, a photon is released. So the flame that we see is essentially the electrons coming back into their orbits, and so there's a plasma there as well. Candle flame is a plasma. All right, finally, a solar flare. Our sun is the gigantic fusion reactor in the sky. It is a ball of plasma, right? Many, many, many times the size of the Earth. A gigantic ball of plasma. So all of the instabilities you see in the atmosphere of the sun, all of these beautiful arcs and loops and things like that our probes, our solar probes have viewed. And by the way, this image is an actual image from a solar probe that we sent to orbit the sun. You can see the beautiful, kind of like the shapes. In other words, the sun is not static either. It's dancing and so on. So I've brought it up 3 or 4 times now that plasma is not a stationary thing. And so we're going to get back to that later. Just kind of put that in the back of your mind. All right, so we talked about the idea of giving examples of what a plasma is. You can see it's around you everywhere. Plasma comprises something like 99.99% of the visible universe because all stars are made of plasma, and also nebula in the intergalactic space, and the galactic space is also plasma. And so most of the matter in the universe is actually plasma. We just happen to live on a cold rock where the electrons have come back into the orbits of the atoms, and so it's not a plasma here, other than lightning and other examples that we talked about. Now, we said plasma is a gas of an ionized gas is what it's talking about. Let's talk about what that is. I want you to understand what a plasma actually is. All right, so we're going to take the simplest atom we have, the hydrogen atom. Now, we can make a plasma with any atom, but we often make plasmas with hydrogen because it's the easiest to work with. In fact, a lot of nuclear reactors, fusion research involves hydrogen because it's a simple atom to work with. And actually, I used to work on spacecraft propulsion systems for basically plasma propulsion systems for spacecraft, and we also used a flavor of hydrogen also for our fuel. But you can use other gases, xenon, argon, you can use all kinds of gases to make a plasma, to make a thruster or something like this. Now, in a neutral atom of hydrogen, in the nucleus, you know there's a proton here, I'll just put a P there, and we have an electron here. And there, for the hydrogen atom, there is one electron and one proton. Now, before I do anything else, I want to tell you that this picture of the atom of hydrogen is not correct. We know from quantum mechanics that an atom is not a little solar system with the electron orbiting. I still draw it this way because if I tried to draw it the way we actually think electrons behave as waves, waves that surround the atom, then it becomes impossible to draw and impossible to visualize, especially with many, many electrons. So we still draw them as little balls, but electrons are not balls, they're waves. Protons are comprised of quarks, and they have similar properties to waves as well. Everything's made of waves. That's an aside, but I just want you to be aware of that because these drawings are not supposed to be accurate. So I guess what I'm trying to say is we use these pictures for visualization because it does help us, but don't take it to the bank as an actual representation of what an atom looks like because it's not, okay? I want to make that upfront clear to everyone. So here is a neutral atom of hydrogen. If I look far away at this thing, there's one positive charge and one negative charge. And from algebra, +1 and -1, you add them together, it makes 0. So from a distance, far away, that single hydrogen atom looks like it has no charge, 0 charge. And if you have 1 trillion hydrogen atoms in a gas tube or in space or whatever, then from a distance it looks like it's a neutral gas. That's why the gases in the room in here or anywhere you walk outside, the wind, they don't behave electrically. Gases don't conduct electricity. There's no free electrons like in a metal where you can conduct electricity easily. There are electrons, but they're all bound to the atom. They don't want to be released from the atom. They're very strongly bound. And so gases don't normally conduct electricity. However, if I could separate these two and make them detached from one another, then I would have charged particles which would not be connected together like this, which could freely move and conduct electricity. And that's what we call a plasma. So if I add energy to this thing, a lot of energy, either in the form of heat or actually electricity, then what would happen? Well, then I would still have my proton here. I'll put a little P there. And I would still have, I'll move it a little farther away, electron here, like this, right? But what I'm going to do is I'm just going to kind of like draw a little arrow indicating that electron's moving over there and a little arrow indicating that proton's moving in a different direction. And there's no orbiting anymore. So this electron becomes detached, right? So I glossed over it, but how could you do this? Well, if you start with, let's talk about solid, liquid, gas. Let's think about it. If you start with ice, solid, and you add heat to it, it goes through a phase change and you get to the liquid state. So in a solid, everything's bound and rigid. You give it enough energy, then they can kind of break out of their positions and start to flow past each other. We call that a liquid. If I add more heat to the liquid, then eventually they become so agitated that some of the atoms or molecules can detach from the liquid and float away. We call that the gas phase. So going from solid to liquid and liquid to gas, all we did was add heat energy. Now, if we have a gas and we add more energy and more energy and more energy, what's going to happen is those atoms are going to go faster and faster and faster, colliding, 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 colliding. And if I add maybe a few thousand degrees of temperature to these to these atoms, what can eventually happen through collisions is that the electron can be knocked free and ripped apart from the orbit, detached like this. And yes, they are flying in different directions. It could collide with another atom or another proton and so on. But if it has so much energy, it won't necessarily come back into orbit. It might just ricochet off and stay separated like this. All right. Now that's how we could do it with heat. We can also do it by putting a very strong electric field into the gas, and that's how we do it in a neon tube or these little plasma balls that you see. We put an electric field there. Now, an electric field is essentially a vector field. Electric field has a magnitude and a direction. And the positive charges that are present are going to want to be pushed along the direction of the arrow. And the negative charges, they want to be pushed in opposition to the direction of the electric field. So if I put an electric field this direction, then the proton's going to want to move this way, and the electron's going to want to move this way. So effectively what's going to happen, if I could put a voltage, another way of thinking of electric fields, a very strong voltage across the gas, the proton's going to want to be pulled this way, and the electron's going to want to be pulled this way. And the stronger the field, the more and more I'm pulling them and pulling them and pulling them. Eventually, if this electric field or voltage gets to be high enough, then they can become detached and separated. That's how the ionization process happens. Once they have been separated, they're cruising around with such velocity that sometimes they'll come back into orbit around another proton, but sometimes they'll just ricochet right off due to the way it collides and stay in the ionized state. All right, so that's what we call a plasma. A plasma is an atom that's been detached like this. Now, if I have a gas tube full of gas and I apply a voltage to it to give it some energy, then at first a very small fraction of the atoms will become ionized. And as more and more and more of the gas becomes ionized, we say that it has a higher ionization fraction, okay? Eventually, if you put enough energy into it, you can make every single atom in the gas tube or in whatever you're talking about become ionized. But it's very hard to do that. It's very hard to get every single atom to be ionized. You have to put a lot of energy into it to make sure that every little electron and proton has enough energy to become ionized, right? So real gases are what we call partially ionized. In that neon tube that we talked about before, the exact fraction is something I haven't calculated or looked up, but it's a small fraction of the gas that's actually ionized. Now here's a fun fact. When you have a situation where you have a gas that's ionized, some electrons are high energy and moving freely through the gas. Some of the protons are moving through the gas, or the charged ions left behind are moving through the gas. But you have a lot of neutral atoms mixed in as well. So in that neon tube, you have neutral atoms of neon, and then you have free electrons running around there. And then you also have the nucleus, the neon nucleus, the ions left behind also running around there. So it's a mixture of all three. So it's almost never a fully pure ionized plasma. You can get that, maybe if you dump a lot of energy into a very small amount of gas, but in general, in these neon tubes, it's just a small fraction of the gas that's ionized. Now, when one of these electrons, through random collisions, approaches a proton in such a way that it doesn't bounce off and kind of re-enters the orbit of the proton, what you get is a photon that's released. So if you have this proton, and originally you had the electron appear, and then it kind of gets close to the sense where in the exact angle and the energy so that it doesn't bounce off or just kind of fly in the other direction, but instead it re-enters orbit around this proton, right? That's called recombination. And when an electron falls in and begins to orbit an atom, a photon is released. And this photon is what we actually see. So when we look at lightning, we actually see the light that is happening from the electrons coming back in and orbiting an atom, right? In the plasma ball, the beautiful tendrils of light that we see, those are the photons coming from electrons going back into orbit around some of the other nuclei or positive ions. In the aurora, the beautiful shimmering pictures of the light, that is coming from electrons going back into orbit. So I guess what I'm trying to tell you, and the same thing with the candle flame. The candle flame, we're seeing the flame, we're seeing the light coming from the electrons going into orbit. So we never see the plasma itself, is what I'm trying to tell you. All we see are the photons that are generated from electrons recombining with the ions. And in a tube where you're putting energy in, you're always reionizing some fraction of these atoms. And then through chance collision, some fraction of them are going back into orbit around atoms and releasing photons. And then the energy we're putting in is, of course, reionizing, and then we're getting recombination, and we're reionizing and recombination. And there's a steady state where we see a light emanating from the substance at a certain rate, because this ionization process is happening and the recombination process is also happening at exactly the same time. So that's the takeaway I wanted you to have. We don't see the plasma. We don't. In fact, if you had a purely fully ionized plasma with a gas tube and you dump gigawatts of energy into it, of power into it, and you ionized every single atom that was in there. In other words, if you had a gas full of hydrogen and you ionized every single atom so that every atom was a free electron and a free proton, and none of these ever recombined because the energy was so high they could never recombine and go back into orbit like this, then we would never see anything. It would look completely clear. So the highest energy plasmas, we don't actually see them. We only see the after effects of the recombination. So the higher energy plasma is completely transparent. That's what I'm trying to drill home there. All right, now let's talk a little bit about temperature of plasmas, because I just find it fascinating. All right, we're going to write down a few numbers and talk about it. We're going to talk about the surface of the sun. The surface of the sun we can measure to be about 5,500 degrees Celsius. Very, very hot, right? And because it's so hot, of course, the hydrogen and helium and things that form in the outer layer of the sun, it's a plasma. Of course it is, because you have some of those atoms, a lot of those atoms that are ionized, but of course, you're having recombination where the electrons are coming back in, like we've talked about here, and that's the sunlight that we see is from the electrons that are coming back into orbit. If the sun were 100% plasma, fully ionized, we wouldn't see anything. I mean, it would still have gravity and all that, but we would literally see nothing. So even though the sun is so hot, we can still see it, and if we can see it, it means that it's not fully ionized. That's what I'm trying to say, right? Let's talk about the sun's core, where the actual fusion happens. That is 15,000,000 degrees Celsius, 15 million degrees Celsius. Now it makes sense that the core of the sun is 15 million degrees, because that's where the fusion is happening. That is how the sun achieves nuclear fusion. The sun is so massive, and it's actually a pretty small star as stars go, but compared to Earth, it's very massive. It has such gravity that the gravity is just pushing in on everything there. And the plasma that is in the core of the sun is a mixture of all kinds of ions and electrons, but just consider it to be protons and electrons. The pressure is pushing on this stuff. And so, see, every time you have a proton colliding with another proton, they're two positive charges and they want to repel each other. Well, the gravity of the sun will take two protons. I'll just draw another one here. Here's another proton. Let's say that it's going this way, right? Well, it's going to collide. Well, the gravity of the sun can push these things together and overcome the electric repulsion between them. You see, it's a common misconception, but the electrical forces of repulsion and attraction are millions and millions and millions of times more or stronger than gravity. We think of gravity as being strong, but gravity is actually the weakest force in nature. The electromagnetic force, the electric repulsion and attraction, is millions of times stronger than gravity. So to take two protons, which are both positive, and push them together and get them to overcome their repulsive nature and to fuse into another nucleus and release energy in the process takes a tremendous amount of gravitational force to overcome that. That's why we don't see stars the size of our moon. You have to have very large objects to have enough gravity to squeeze these things together and make them fuse. That's kind of a lecture for another day, but interesting nonetheless. So 15 million degrees, that's why. That's why you have so much temperature there, because the gravity is pushing on everything and causing everything to move so fast. The high-speed collisions that are happening there are overcoming the repulsion of the protons to fuse and form helium nuclei and so on. What about lightning? Any guesses for lightning? Lightning roughly is 20,000 degrees Celsius. So, and actually it varies, because some lightning strikes are very intense and super intense. There's nothing else, no other way to say it. Some lightning strikes are just not as intense of a discharge. but you can say that 10, 20,000 degrees Celsius. Notice that the temperature of lightning is actually hotter than the temperature of the sun by a big margin, but it's nowhere close to the center of the sun. The center of the sun where fusion is happening. Obviously, lightning is not going to be hot enough to achieve fusion, otherwise we'd be fusing ourselves out of existence all the time. But it's extremely hot, hotter than the surface of the sun by several times, right? And that is a lecture for another day, why lightning gets so hot. We'll talk about how it happens, but it all comes down to the electromagnetic force, or the electric forces between ions. All right, so let's talk about something not quite so hot. Candle, flame. Somewhere around 1400 degrees Celsius. So not as hot, but certainly hot enough for some of these electrons in the gas that's burning to become detached and then recombine and emit a photon. So you can see that all these are considered plasmas. Now let's talk about another kind of plasma that you've seen before. A neon sign is what we call it, right? Now a neon sign is a little bit of a misnomer because neon is the most common that produces the orange, kind of red-orange light that we see, but you can put different gases in these tubes and achieve different colors. You know, argon is used a lot, xenon is used. All of these gases will generate different colors when you ionize them, when the recombination happens here. But let's talk about neon for a second. Neon sign. And this is interesting, right? In a neon sign, or in a neon sign, or also in a fluorescent bulb, the same thing has happened. Fluorescent. Fluorescent bulb are these long white lights that are in the ceiling, right? What's going on is there's a gas in there. We ionize the gas. When the photons come out of that, then they hit the inner surface of the tube, which is coated with a phosphorescent substance. That's why it's called a fluorescent, or a fluorescent substance. And then we can turn those photons into visible light, because a lot of the light that comes out of these gases are in ultraviolet and other energy ranges. But when we coat the inside of one of these tubes with one of these substances, we can turn that into visible light, safe light for us to look at. But if you look on the inside of our fluorescent bulb and actually do the analysis, the electron temperature of the electrons in the plasma inside of that bulb is on the order of 11,000 Kelvin. Now, I know I mixed units here because I'm talking Celsius and Kelvin, but the difference between Celsius and Kelvin is only about 300 degrees. So Celsius and Kelvin, when you're talking about numbers this big, they're almost exactly the same thing. So you can call it 11,000 Celsius if you want to. So how does that reconcile with the idea? I know you've all seen these fluorescent bulbs or these neon signs. We can touch them. I mean, they're warm, but we can certainly touch them. It doesn't feel like 11,000 degrees. So how can that be? You see, you got to be careful when you talk about plasmas. When we talk about the temperature of an object, what do we mean? We're really measuring the average kinetic energy of, in this case, electrons, the electrons in the plasma, in this fluorescent bulb. And what it means is when we ionize and you have a free electron, it has so much energy. When you convert that to a temperature measurement, it's around 11,000 degrees. But I told you at the beginning of the lesson that in these plasmas, there's only a small fraction of plasma that's actually there. The rest of it is neutral atoms. So the reason that we can touch the bulb is that even though all the electrons have a very, very high energy, it's only a very small percent ionized. In other words, there's a very small number of electrons with that temperature. Yes, when those electrons hit the wall of the tube, they do impart their energy and it does make the bulb warm. But it doesn't get hot and it doesn't melt the bulb, because with 11,000 Kelvin would melt anything, right? Or anything that we would put in a bulb. The reason it doesn't melt it is because there's just not that many electrons there with that temperature. Most of the gas in the tube is always neutral. Most of the gas in these neon signs are still neutral atoms with a small fraction that are ionized. Now the ones that are ionized are moving very, very fast with a very high temperature. You know, but there's so few of them that the bulb gets warm but not hot. But in fusion reactors, which is what we're really trying to use plasma for, that becomes a different story. We have to be very careful not to melt the entire thing down, because we're trying to create plasmas with a very high ionization fraction and also with a very, very high energy. So we have to try to contain the plasmas in a magnetic field, in a magnetic bottle of some kind, because the walls of the container for a fusion reactor, prototype design that are being built now, they would actually melt if the plasma touched or bounced off the wall. So we have to use magnetic fields to try to contain it. All right. Now I've drawn this plasma for hydrogen, but I want to make sure you understand that it applies, the idea of a plasma applies to any element, okay? You don't have to have hydrogen, it can be anything else. So let's just talk about the element neon real quick. It'll only take a second, and I think it's good to have more than one example. Neon has 10 protons in the nucleus, if you look on the periodic table, and has 10 neutrons, which are neutral. And I'm going to draw a circle around that because those are all in the nucleus in the center. Now, if there's 10 protons, there has to be 10 electrons orbiting neon. So here, let's do 1, here's 2 electrons here. Again, I'm drawing it as a solar system, but we know the electrons really are not little balls like this. I'm just drawing it so you can visualize it. All right, so there's 2. Here's 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, and then here's 9, and then here's 10. So these are all electrons. I'm not going to write all the little e's around here, but these are all electrons here. Now you got to be careful because this is not a chemistry class, and so I'm being a little bit sloppy in my diagrams, and I don't want anybody to be confused. So what happens here is these inner 2 electrons, these are in the n equals 1 energy level, and then these electrons, which are farther away, are in the n equals 2 energy level. But just so you know, when you take chemistry and physics, you learn that these electrons, they're not orbiting like this. They're really waves, and even inside the same energy level, they have sort of different shapes for the waves. We have the s orbitals, and the p orbitals, and the f orbitals, and the d orbitals. I'm not drawing any of that stuff. I'm just representing that there's 10 protons, 10 neutrons, and 10 electrons around this xenon atom, or this neon atom here. And we can arrange them in the energy levels, but I'm leaving out a lot of the details of the wave structure of the electron because it's not important for this discussion. Now, if I apply an electric field to this, I can do it anywhere, but I could literally just draw an arrow to the right and call it electric field. That would be the same as like a voltage applied across this gas. Then all the protons are going to want to go in the direction of the electric field, and all these electrons, especially the ones on the outside, which can feel the electric field more, they're going to be going the other way. So we're trying to rip the atom apart. If I make this big enough, one of these electrons will be literally ripped apart, and then from the atom. And then what would I have? I would have a free electron running around the plasma, and what would be left behind would be a neon. It's still neon, but it will be a neon ion. That's what an ion is. It's an atom that's lost an electron, or we can also have atoms which gain extra electrons. Anyway, it's an atom that is charged. If we take an electron away like this, the neon atom will have an overall positive charge because there'd be 10 protons and only 9 electrons. So it'd have a charge of +1. And so we'd have a positively charged neon ion and a negatively charged electron. That would be in the mixture of all the other neon atoms in the gas, and so it would be an ionized atom and make a plasma. And the more of these pairs of ions and electron we have, the more of the gas is ionized. Now the first electron is pretty easy to remove. The second and the third and the fourth and the fifth electron are much, much harder to remove because once you take the first electron away, the nucleus can attract all of the remaining electrons a lot more strongly. So it's physically harder to remove the second electron. We call it the ionization energy. Very hard to remove the second electron and the third and the fourth to make a more ionized plasma. Very difficult to do, but you can do it by dumping more and more energy into it. All right, I just wanted to bring that up because I didn't want you to think that all plasmas have to be hydrogen. Any atom, you take an electron away, then you have electron running around and an ion running around, makes a plasma. And you can do that, you see that in the neon sign and all kinds of other situations. Now here's I saved the best for last. I do want to talk to you about this. We could probably end the whole lesson. I already taught you what a plasma is and gave you examples. I could just say, okay, it's done. But that would be leaving the dessert off the table. I don't want to leave the dessert off the table. The dessert's the most fun part. Okay, I want to talk about why plasmas are interesting and amazing and hard to deal with. Because ultimately what we want to do is make a fusion reactor. We want to be able to make clean energy. A fusion reactor combining hydrogen nuclei together would generate almost unlimited amounts of clean energy. No radioactive waste, right? No real risk of a meltdown if you design it properly, right? You don't have to worry about uranium and other radioactive substances, plutonium and things like that are radioactive. None of that stuff is part of it, but the downside is to build a fusion reactor is much, much harder than the original physicists thought. when we proposed it, right? Much harder because plasma is harder to deal with. Now, when I worked in this field, the common phrase was that controlling a plasma is kind of like controlling Jell-O with a piece of string. Imagine Jell-O in a bowl, and I want to take the Jell-O out of the bowl and put it into another bowl. But I don't have any spoons, and I can't use my fingers. I only have a piece of string. So I lift it, and I try to like put it in there. You can see the string is going to go right through the Jell-O. And it's going to be very difficult to get it to do what you want it to do. And that's the problem with plasmas, is because they're electrically conductive, they're very, very hard to manipulate. Now, I'm going to do some talking here. I'll draw some pictures, but let me tell you the main upshot. We know that positive charges and negative charges, they make their own electric fields. That's what an electric field is. It's a field emanating from a charged particle, a positive charge or a negative charge, like an electron or a proton, right? So in the drawing over there with the protons and the electrons, they emanate their own electric fields. And we also know that when charges move, like electric current, they generate their own magnetic field. So charges, when they're stationary, make their own electric field, and charges, when they're moving, make their own magnetic field. Let me make sure I said that correctly. Charges that are stationary produce their own electric field, but charges, those same charges that are in motion, also generate a magnetic field. But then we also know that electric and magnetic fields impart forces to all charged particles, electrons and protons. So you see why all the instability happens in all these pictures that I'm showing you of plasma. Because all of those charged particles, electrons and ions that are there, electrons and protons, whatever's in there, they have associated with them electric fields that they're producing. And those electric fields are pushing on all the neighboring charged particles, making them move. But as soon as they begin to move, they're also generating magnetic fields. And the magnetic fields are also pushing on all the other particles around them. But the magnetic fields push in a sideways direction. That's the little bit I haven't told you yet. Electric fields push along the arrow, but magnetic fields push perpendicular to the direction of the magnetic field. So all of this plasma gets wavy and crazy with instability because as everything begins to move, it generates its electric and magnetic fields, which are pushing on all the neighboring charged particles. But once the neighboring charged particles begin to move, they generate their own magnetic fields, which then push everything else again. And so it generates all these instabilities. So when you try to contain it with a magnetic field and make it fuse, then it becomes difficult because it tends to resist what you're trying to do. So one little picture, and then we'll wrap it up. All charged particles, for instance, here is a proton. From this proton, spontaneously, without anything on our part, it emanates an electric field. Right? Whoops, not like this. The electric field goes radially out from the particle. I could draw more arrows if I wanted to, right? And the same is true of negative charges. You could have an electron right here. Here's an electron. Except the electric field doesn't emanate radially outward. The electric field actually radiates inward towards electrons. But you can see that the arrows go straight in and out of all the particles, right? Now, these electric fields that are present here, if I take another proton and place it here, this electric field will push it along the field lines here. If it's a positive charge, it'll push it this way. If I place an electron here, it'll go against the arrow. So, yeah, and you can see the arrows are acting here. If I put a positive charge here, it'll go towards the arrow, towards being attracted to the nucleus. But if I put a proton, if I put a proton here, it'll go towards the nucleus. If I put an electron here, it'll go against the arrow, trying to be repelled away from the nucleus. But as these things begin to move, they generate also magnetic fields. So if I have a positive proton here, and then it moves this direction, that's what we call an electric current, essentially. And so the proton is ends up being like right here. As soon as the thing starts moving, we have this thing called the right-hand rule, and it generates a circular magnetic field, which kind of, from the right-hand rule, your thumb goes in the direction of the current flow being the proton that's moving here. And so my fingers are curling this direction. So there's a magnetic field, which is like a donut that goes all the way around this moving charge. Okay, so the electric field, which is always here, is pushing on any particles that are there. But as soon as the particles begin to move, they generate their own magnetic field. The magnetic field also pushes on all the charged particles, but it doesn't push along the direction of the arrow, it pushes perpendicular. I'm not going to draw it on the picture because it'll get cumbersome. But just know that magnetic fields don't push in the direction of the magnetic field, they push sideways. So it kicks them out sideways. So you see how this can lead to instabilities. As soon as any plasma particle, proton or electron, begins to move, it generates a magnetic field which pushes any adjacent particles in a sideways direction. And then when they begin to move, the ones that are then pushed are generating their magnetic fields as well, which pushes everything, including the original ones, in a different direction. And then you have electric fields on top of it. And then on top of all of that, you have all of the normal considerations of fluid equations, fluid mechanics. So in a plasma, not only do you have to understand how fluids behave, all the equations of fluid motion, pressure and density and turbulent flow, vortices and things like that in a fluid, but you also have to understand how electric and magnetic fields of these particles interact with each other. And so that leads to all this waviness and instability. And that is why plasmas are difficult to control for fusion and for rocket propulsions and things like that. But we're still working on it because the goal, the end result of the goal is going to be worthwhile. When we figure it out, and we know fusion can work, the sun is in the sky, we just have to be able to build a reactor on the ground that can generate this kind of power, which will be clean for us all to use. So that was an introduction to plasmas. I know it was a little bit long, please forgive me for that. I could cut half this lesson out, but then I'm like, you're missing out on all the fun stuff. Why is it interesting? Why do we care? How is it in everyday life around us? I don't want to cut that stuff out. So I appreciate you sticking with me to the end. I hope I've encouraged you to go learn more about plasmas and other topics in science and engineering.